I'd like to welcome everybody to the third session of our fall program. And today we'll have Amir and Sophia Rupp presenting their work. So each presentation will be about 20 minutes, and we'll have about 10 minutes after each presentation for questions and any comments from the audience. So really encourage communication here and participation. I'd also like to point out that this is being recorded. So the recording of this will be made available after on the VISIM website. So thank you all for attending. Now I'd like to introduce our first speaker. So Amir is a PhD candidate in the Civil Engineering Department at Toronto Metropolitan University in Canada. He holds bachelor's and master's degrees in aerospace engineering from Sheriff University of Technology. And under the supervision of Dr. Arnaud Duan, his research focuses on risk-informed infrastructure lifecycle planning. Currently, he is working on developing a multi-agent deep reinforcement learning framework for adaptive inspection and maintenance plan optimization for infrastructure networks, which I'm sure we're going to get to hear all about now. So with this, I'd like to pass it over to Amir.
Thank you, Adrian, for the introduction. Let me share the screen. Okay, can everyone see my screen?
Yes.
Okay, thank you. The title of this presentation is Infrastructure Network Maintenance Planning using a Deep Reinforcement Learning Approach. I'm Amir, PhD candidate at Toronto Metropolitan University. For this presentation, first, I want to introduce the background and motivation of this study. After that, I'll go through the problem definition and the formulation. And then I introduce the reinforcement learning approach. After that, I present the results and the discussion. Infrastructure systems are subject to various situation mechanisms that affect both structural and operational conditions. And Canada's infrastructure deficit is estimated to be up to $570 billion. And based on the Canadian Infrastructure Report, which the last version is 2019, 30% of water mains and sewer is in a fair and worse condition, and the situation is not also good for roads and bridge. 40% of them are in fair and worse condition. So by considering the situation for infrastructure and also the limited resources to address the aging issue, we will see that we need to optimize life cycle management policy to use our resources, take advantage of our resources better. Actually, the motivation of this study is the network sequential decision-making challenges. For sequential decision-making, especially for the networks, larger scale networks, the formulation and computation cost is one of the main challenges. For most cases, we cannot formulate the problem in a linear setting to take advantage of linear programming. And also the heuristic algorithms are evolutionary algorithms such as genetic algorithm cannot help much because they are case specific and also they may have convergence issue. The motivation is one of our projects. We have about to optimize the sewer network flushing program for municipality in Ontario, Canada. And in the right-hand side, you can see the sewer networks. The sewer network consists of almost 2,000 sewer segments and 21 catchments. Each catchment consists of many sewer segments. Here you can see the sewer catchment. Actually, catchment is a sewer shed. sewer catchment in different colors, and each catchment almost consists of about, on average, 100 segments. Here, as from one of the operational assumption, if we want to flush a sewer segment, we need to flush the whole catchment. Then we can consider this decision-making problem is a system of 21 components, because each component, each sewer catchment is a decision unit, and if we want to flush one catchment, it means we flush all the sewer segments in the catchment. So we can formulate our problem. Here you can see different years. Each year is a decision step. For example, for 7 years, we have 7 decision steps. And at each stage, we need to decide which catchments should be flushed at that year. And in this study, I consider a toy example with 7 catchments and 7 years. It means we have 49 binary decision variables for this problem. Each xij is a binary decision variable. 0 means we do not flush that catchment, and 1 means we flush that catchment for that specific year. We model the problem as a Markov decision process. The condition of each sewer segment is defined as a 5-scale rating based on NASCO PHCP rating, which 5 is worst condition that needs replacement, and also 1 is the excellent condition. And so the deterioration mechanism can be modeled as a Markov process. Here in the left-hand side, you can see the transition metrics for natural deterioration, and M is the maintenance effectiveness metrics. And for example, you can see for the catchment 1, for the first catchment, the transition probability metrics that present natural deterioration. And also here we consider perfect maintenance, which means whatever is the state of the catchment after flushing, it goes to the excellent state. And this assumption won't affect the performance or algorithm, because it's just a transition metrics. We can consider any metrics effectiveness metric, but because of lacking of data, we consider perfect maintenance here. The goal of this optimization is to minimize the overall average condition of the sewer network for the whole planning horizon. It means we need to minimize the performance of each catchment. Actually, it is a weighted average, and the weights are the length of the catchments over the 7 years. Li is the length of the catchment, and H is the planning horizon, N is the number of catchments, and mu ij is the overall condition of catchment I at the end of year J. Here you can see the mu ij, which is the performance or the overall condition, is the expectation of a state vector of the catchment after action I for catchment I at year J when we apply the action. So we can define the state vector based on the action and also the state vector from the previous year. As you can see, overall the overall condition for each catchment at a specific year is a function of transition matrices and also the decision made in the previous years. So as we need to take multiple decisions for each catchment, it is not a linear function of decision variables. So this is one of the challenges. We cannot formulate the problem in a linear format. With some assumption, we can, for example, if we just consider one action per components, then we can change it. But it is not the case because it is not a realistic assumption. Here you can see the constraints. One constraint is the total budget. The whole flourishing program cost should be less than a specific budget considered for this problem. The next constraint, which is very important, is the annual budget tolerance. Here, the cost of each year, program of each year, should be within a specific tolerance from the average budget, average annual budget. And for example, in this problem, we consider 15% tolerance, which means the annual budget can be from less than 15% of the average budget to up to 15% more than the average budget. The next constraint is that all catchment must be flushed at least once in this program to make sure that all network will be covered during this program. Since our problem is a Markov decision process, I consider to use a reinforcement learning approach to solve this MDP. In a reinforcement learning setting, we have an agents that make action in the environment. And after each action or after each decision, the environments transit agents to the next state and also give the agents a reward as a function of the state and the action which has been taken. In reinforcement learning setting, the goal is to maximize the total cumulative discounted reward or the negative of cost, or it is equivalent to minimize the cumulative cost. Here, gamma is the discount factor and R is the reward of each action in a specific state. And here, GT is the total cumulative reward during this program. There is an important concept here, which is action value function. And action value function means how is good to take a specific action at in a given state. And it is the expectation of the upcoming reward, expectation of future reward after taking a specific action in a specific state. The foundation of reinforcement learning is dynamic programming. However, in dynamic programming, we need, if we want to estimate the value of a state, we need to take the expectation all over possible future states for the next stage. But many reinforcement learning algorithms use temporal difference backup. It means you make estimation gradually by interacting in the environment, and just with one step forward, that you after acting, making a decision, you see the next state, and also you see what is the reward, and based on that rewards, you gradually learn the value function of the states or action value of function of the policy. Here I use a Q-learning algorithm. In Q-learning algorithm, first we initialize all the Q values, and then we start interact in the environment within a specific training episode. For example, here I use 50,000 training episode, or each episode is a simulation from the first year to the last year. we consider epsilon greedy policy. I'll explain it later. And after when we interact in the environment, for a specific state, we take action based on the policy, and then we see what is the reward and what is the next state. And based on that, we update our estimation about the Q values for that specific state and action. And here, epsilon greedy means at each stage, we take with epsilon probability, we take random action, and with 1 minus epsilon, we use our previously learned policy. Actually, this is because here we have a exploitation dilemma. To address this, we use epsilon greedy policy, and as we go through the environment, through the learning, we decrease the epsilon. It means gradually we take advantage more of the learned policy to reinforce it. But where this deep word for deep reinforcement learning come from, and why we need a deep neural network in reinforcement learning? It is because of many reasons. For large state action space, for large MDP, it is not practical to create a table for all possible state action pairs. For example, for a problem for the full network for 21 catchments, even if you want to create a empty table, then you have not enough store on your RAM. It needs around 1 terabyte of RAM on your computer, and it is not possible. And also sometimes the state space is continuous, the same as here, as the condition of each catchment is an expectation based on the state probability vector, then it is a continuous. And also sometimes we need generalization from seen states to unseen states. So it is good to have a function that estimates the Q values. And here, consider this black box as a function with specific parameters, vector of theta. And when we pass a state to this function, it gives the Q values of each state action pair of that state for all actions. And our goal through the training process is to minimize the loss function of this from the predicted values and estimated values through the training process. And then we need to just optimize the parameters of the function. For this problem, the state vector is defined as 9 elements. The first 7 elements is the conditions of the catchments, which is from 1, the real values from 1 to 5. And also the 8th element is the year, and the last one is the remaining budget, which is the proportion of budget from 0 to 1. The reward definition is the reward is defined as a 5 minus the overall conditions of the network after applying the action based on the transition metrics. And also I added a negative value to the last step reward if the total cost exceeds the total budget. And we can deal with the annual budget in 2 ways. As naive assumption, we can, if the annual budget is out of the specified range, out of the tolerance, then we can add a penalty to the rewards. The next option is we reduce the action space because for this example, we have a 7 catchment. It means 2 to the power of 7, we have 128 catchments, 8 actions, excuse me, in the action space. but based on the annual budget tolerance, 14 of them is feasible actions that won't violate the annual budget constraint. Here is the deep Q network proposed for this algorithm. You can see the system state vectors consist of 9 elements, 9 nodes. Also, the first, I use a double hidden layer. Each layer has 16 neurons, and the last layer is the action space. If we consider full action space, it is 128 actions, and with the action reduction, we have 14 nodes here. And through the forward path, we calculate the outputs of this neural network, which is the state action values, and also the loss function. And through the backward path, we update the parameters of this neural network. Here you can see the results for the toy example, which is 7 catchments and 7-year plan. And I trained this agent for 15,000 episodes. You can see how in the left chart, you can see the total cumulative reward during the training period. You can see some jumps because it is the epsilon greedy policy. Sometimes it take action based on the random action. And in the middle chart, you can see how the epsilon decay through the training. And the right-hand side, you can see the chart of greedy policy results during the training process. Here you can see the results for the network with 7 catchments and 7 years. The objective value would be 2.408, and the total cost is around 69,000. You can see which catchment should be flushed at which year. And here at the bottom, you can see the budget profile we need for this flushing program. Actually, it is the results of the reinforcement learning, deep reinforcement learning with action reduction based on the annual constraints. Also, I consider the multi-agent reinforcement learning. One of the problem of a single agent is the limitation is the action space when you have multiple components. Here we can consider separate decision maker for each catchment. So we have just 2 actions for each agent, and we can consider separate tiny network for the agents. And the agents cooperate toward the shared objective. And the reward consists of both a system and agent specific rewards. I want to compare the results of this multi-agent to the previous one. And also to compare with evolutionary algorithm, here you can see the chromosome for the genetic algorithm. It is based on the binary decision variables. We have for each catchment, we have 7, because we have 7 years, we have 7 elements, decision variables. And also for that, I use a deep Python library for evolution, which is a novel platform for evolutionary algorithms. And here you can see the results in the solution landscape. For this toy problem, we have more than 10 million feasible solutions. All of these blue dots is a feasible solutions. I actually calculated them with the constraint programming with OR tools, which developed by Google. And also here in the table, you can see the objectives of different algorithms. The optimum solution, which I calculated with constraint programming, is around 2.4. With deep reinforcement learning with action reduction, I got 2.408. You can see the different solution in the solution landscape. And also the worst one is for multi-agent deep reinforcement learning, because there is a challenge to define how the agents cooperate together to reach the solution. It needs a hyperparameter actual adjustments. It needs more work to reach a good solution. And that's it. Thank you for listening. If you have any question, I'm glad to answer you.
Thank you. Really interesting presentation. So I think, does anybody have one question? We can take one and then go on to Sophia's talk, if that's okay.
Hi, I have a question. So have you tried this in the larger network other than the 7?
Actually, I adopted this example because I want to check what is the solution landscape. This chart, this is the, actually, I can just find the old feasible solution based on constraint programming. It is the largest example that I can get the all feasible solutions to see how much the algorithm is far from the optimum solution. This is why I choose 7 catchments for a toy example. But I can check. I haven't tried this algorithm on the larger network yet, but the reason, as I said, I choose this example because I cannot find all the solution for larger than it is interactable.
Yeah, I understand that, because I think for the network with 7 catchment, you already have like so much feasible solution, and I feel that it will like explode with the larger network. So yeah, thank you so much.
Thank you.
Thank you. So in the interest of time, I'll go ahead and introduce Sophia, our next speaker. So Sophia Rupp is currently a civil engineering master's student with a concentration in structural engineering at the University of Delaware. Her master's research is focused on studying advanced applied materials for existing concrete bridge rehabilitation and strengthening. Sophia obtained her bachelor's degree in civil engineering at the University of Delaware while assisting on a research project focused on comparing different US state load rating procedures for bridges or culverts with missing or incomplete as-built information. She hopes to continue researching on the current bridge rehabilitation and strengthening materials she's studying, or research new materials in industry after graduating from the University of Delaware. So with this, I'd like to hand it over to Sophia.
Thank you, Adrian. Can everybody see my screen okay?
Yes.
All right, so as Adrian mentioned, my name is Sophia Rupp, and I am working with my advisor, Professor Yvonne Tatar, studying a material that's known as carbon fiber reinforced polymer, or CFRP for short. And we are specifically looking at improving the durability of externally bonded CFRP composites with fiber anchors. So before I get into the details of my research, I'd like to start with a brief overview of all the topics I'll talk about in this presentation. I'll start with an introduction and explain where FRP is typically being used right now. I'll give a background on the material itself and how FRP is applied, or what's also known as the strengthening process using FRP. I'll talk about the motivation of my research and why it's important. I'll talk about the study design, the methodology that we plan to use to meet the research objectives that we established, the test variables, the fabrication of my test specimens, the setup of my experiment, and then finally the current results that I have. As I'm sure many of you are well aware, the bridges that we currently have, or a large portion of the bridges that we have in the nation, are relatively old and they were constructed a very long time ago. And with age of these bridges comes deterioration. Signs of this deterioration are really starting to become evident, especially in the ASC 2021 Infrastructure Report Card, in which they give the nation's bridges a grade of a C. And considering that repair of these bridges is typically, in most cases, the more desirable option over reconstruction, FRP has become the material of choice for repairing these deficient bridges. For those of you who aren't familiar with what FRP is, it is a composite material that consists of two components. The first component is the fiber reinforcement, and then the second component is the polymer matrix, which surrounds the fiber reinforcement. The point of the fiber is to provide strength and stiffness for the composite material, and then the polymer matrix has a few different types or a few different purposes for the composite. The first being that it provides a encasement for the fibers so that water can't get exposed to the fibers, making it corrosion resistant. It also ensures that the fibers stay aligned in one direction, making them unidirectional. And lastly, it ensures that the stresses in the fibers are transferred evenly throughout the composite material. And one thing that I also like to point out, besides it being corrosion resistant, is that it also has a very high strength to weight ratio. Not only can carbon fibers be used, however, that is what I'm specifically looking at for the purpose of this research, but there are other fibers that can be used, such as basalt or e-glass. Although my specific type of carbon is not shown here in this modulus of elasticity plot, it would lie between basalt and high strength carbon. And from that, where you can see it has a very high modulus elasticity. It has a modulus of elasticity in order with steel, which is why it is a good alternative to steel for repairing bridges. One thing to also point out is that it is a very brittle material in comparison to steel. It doesn't have those ductility properties. However, for the purposes of its other properties, it is a good alternative for repairing bridges, as I mentioned. There are a few different methods that can be used to fabricate CFRP. The method that I'm specifically using in my research is known as wet layup, or to put it in simpler terms, it's just fabricating the CFRP using your hands. And the way you start this process to apply it and to strengthen a concrete member is to first cut your fibers, your dry fibers out, depending on how much you need. And then you can mix your neat epoxy and your putty epoxy. Neat epoxy consists of two components. It consists of a part A and a part B that need to be proportioned and then mixed together. And then putty epoxy, or what is also known as thickened epoxy, consists of the neat epoxy mixed with silica fume. After you have those components mixed, you can then prepare your surface for applying the CFRP. This consists of applying an initial epoxy primer coat onto the surface. And then on top of that, you apply that thickened epoxy or that putty epoxy on top of it. And what this does is it fills the voids and the pores in the concrete to ensure a good bond between the CFRP and the concrete. And then comes the actual preparation or actual saturation of the fibers to make it a composite material and apply to the concrete surface. This is typically done with a wet layup process of just pouring the mixed epoxy onto the dry fibers and using a tool to make sure that that epoxy has fully saturated each and every fiber. Next is to then take your saturated fibers and apply it to your concrete surface, and typically take a putty knife, drag it over the saturated fibers to make sure that there's no air trapped underneath the saturated fibers or in between the concrete surface and the fibers. And then you let this sit and cure for about 72 hours, and the saturated fibers will then cure and become a composite material, leaving you with a strengthened member. Despite all of the great properties of CFRP that I previously mentioned, there has been prior research done that has shown when CFRP is exposed to water in the field, it will lose adhesion between the CFRP and the concrete. When a strengthened member is subject to flexure and it's dry, we typically will observe a cohesive debonding failure, which indicates that there is good bonding between the CFRP and concrete. However, when it's wet, we will experience a adhesive debonding failure, which indicates that there's poor bonding between the CFRP and concrete, and the CFRP essentially peels away from the concrete. Debonding is a very typical failure mode that we see when a strengthened beam is subject to flexure. So the fact that water exposure can, debonding is a very typical failure mode, and it's very undesirable because it happens way before the CFRP can reach full potential and full use out of its properties. So the fact that water exposure can induce this failure mode makes it very important to research ways to improve the bond durability between CFRP and concrete after it's been exposed to water. And for that reason, that's why I am specifically researching how carbon fiber splay anchors can be used to improve the CFRP and concrete bond after it's been exposed to water. And not only will I be researching the effects of water exposure on a concrete strengthened beam, but also the individual constituents that are strengthening the beam, such as the CFRP alone and the paste epoxy the putty epoxy that I mentioned, and the neat epoxy that I mentioned earlier. ACI 440.9R provides accelerated conditioning protocols, or what for short ACP, that provides guidelines on how you can replicate long-term water exposure to a concrete strengthened beam. And the two main guidelines to take away from this is that the concrete strengthened beams need to be exposed in water for 3,000 hours, and the water that they're immersed in has to be around a temperature of 122 degrees Fahrenheit. And in order to study the strength retention of these beams that have been exposed to water, we also have to have a duplicated group that is unconditioned or is kept in standard laboratory conditions, or SLC for short. And not only will we be immersing the concrete strengthened beams in the water, but we will also be immersing the constituents that make up the strengthened beam to evaluate the effects of ACP on those materials as well. We will be measuring the strength of both the SOC and the ACP groups by doing a 3-point bending test. The beams that I casted so far are 6 inches high by 6 inches wide by 20 inches long. And when they are applied to the 3-point bending test, they will have a clear span of 18 inches. There will be a point load applied on the compressive face, or the compression face of the beam at midspan. And on top of this, there's also a notch introduced at the tension face at the center line, so that we can control crack initiation. From this test, we will be able to collect information about load versus deflection. And on top of that, we will be able to collect strain data from the CFRP. The CFRP gauge will be applied on the CFRP sheet, and it will be applied over that crack that's introduced. There will also be dynamic mechanical analysis tests completed, or DMA for short, in which we will apply a cyclic load to the sample that's being tested, which in this case will be the neat epoxy and the putty epoxy. The cyclic load is applied as the temperature is increased, and this is so that we can characterize the glass transition temperature of the samples, or TG for short. The glass transition temperature is a characterization of when the sample goes from being a glass-like state to a plastic or a rubbery state. And the reason that this is important information to have is so that we know the upper service limit temperature of the material. And then lastly, we will also be conducting tensile tests on the CFRP samples, as well as the putty epoxy and the neat epoxy, to gain information about those mechanical properties. There are a few different variables that I'll be looking at changing and varying throughout my test specimens. The first is the anchor diameter that we're using for strengthening. We are looking at using a 1/4 inch, a 3/8 of an inch, and a 1/2 inch diameter anchor. On top of this, we will also be varying whether the CFRP is bonded to the beam or if it's unbonded to the beam, to give a little bit of a better description on that. A bonded beam will include direct bond between the CFRP and concrete, whereas the unbonded beam will have what is referred to as a bond breaker between the CFRP and the concrete. In my case, I'm using a very thin layer of Teflon tape, and this is so that we can study the anchor capacity alone. And then the last variable that we're looking at is whether or not we include that layer of putty or not over top of that initial epoxy coat. And the reason for that is to see just how effective the use of that putty is in increasing the bond durability or increasing the bond between CFRP and concrete. Before I could actually get into the actual strengthening of the concrete beams, there were a few steps that I had to take in order to prepare the beam for strengthening. As you can imagine, for the beams that had anchors installed, I had to drill holes into the beams. And not only that, but I also had to chamfer those holes to avoid stress concentrations when the fiber splay anchor was bent over that corner. And for the same purposes, I also had to chamfer the corners of the beams. And the reason for that is because we also apply what is known as shear wraps around the sides. And that's just to ensure that the beam will fail in flexure rather than shear. As I mentioned, we introduced that notch in the center line. And then finally, you sandblast the surface of the beam to give it a surface roughness so that there's good bond between the CFRP that's being applied and the concrete. And then comes the actual strengthening process. So I briefly touched on the first two steps here, but I'll summarize them again. In order to strengthen the beam, you first start with an initial neat epoxy primer coat, and then you apply that layer of putty epoxy on top, so long as you are strengthening a beam that includes that putty layer. If you are strengthening a beam where you skip that putty layer, you would then move on to the third step. And additionally, if you're looking at fabricating or strengthening an unbonded beam, you would skip those first two steps and you move on to just applying that Teflon tape, and then go ahead onto the third step, which is saturating your CFRP or saturating your carbon fiber, applying it to the concrete surface, and then going ahead and embedding your anchor into the anchor hole, splaying it out over the CFRP that was applied. And then finally, you add those shear wraps around the sides, and additionally a square patch over the anchor and the anchor hole to give it more of a finished look. This is the accelerated conditioning setup that my lab manager and I came up with so that we can follow the guidelines specified by ACI. It consists of a very large cooler that, as of right now, has all 33 of my ACP beams immersed inside it. There is an inlet and an outlet that has, or an inlet and outlet that is connected to a circulation heater and a pump. This keeps the water consistently circulating in and out of the tank and through the circulation heater to keep it at that specified temperature that ACI requires. These beams are scheduled to begin testing in January 4th, and I'll wrap up testing of those beams by February 6th. Now, considering that those beams have a while before they can be tested on, they're in the process of being conditioned. And additionally, I'm in the process right now of preparing my SLC group of beams for strengthening. I had the chance to work with an undergrad student, Nico Zawadny, and run some preliminary tests on a few SLC beams. The SLC beams consisted of an unstrengthened group, a strengthened group with no anchors, and a strengthened group with anchors, varying those anchor diameters that I mentioned earlier, as well as an unbonded beam with 1/2-inch anchors. As you could imagine, from 3-point bending of the unstrengthened beam, we saw a relatively low load capacity. The tensile cracks started to form pretty early on, and then the beam failed. However, for the strengthened beam that had no anchors, we saw a slight increase in load capacity. And once that initiation of debonding starts to happen, you see a slight increase in stiffness and a slight increase in load. But however, the progression of debonding will continue, and those tensile cracks in the concrete will start to form once it really starts to debond, and that will lead to failure eventually. And then for the beam that was strengthened with fiber anchors, you do see that initiation of debonding around the same load as you do for the beam without anchors. However, after that initiation of debonding starts to happen, you see a very significant increase in stiffness in the member, as well as increase in the load. And this is due to the fact that the CFRP starts to debond, and then the stresses from the CFRP start to transfer to the anchors and into the concrete. And the beam will continue to take load until most likely the anchors fail by anchor pullout, which is when the anchor pulls out of its hole, or the CFRP will rupture around the anchor hole. This is a little bit of a better representation of all the beams that we tested and the strength that was reported for those beams. We found that there was around a 37% to 100% increase between the anchored beam to the unanchored beam. And one thing that's very interesting to point out here is that we didn't see really any significant differences between beam strength for the differing anchor sizes. That's not something we expected to happen, and it's something that will be interesting to see if that still holds true for the accelerated condition beams. And as I mentioned, not only do we measure the strength of the beams, but we also measure the strain of the CFRP when we load it in 3-point bending. So we found that there was around a 500% to 700% increase in strain utilization between the anchored and the unanchored beam. But however, I would like to point out here that we're not sure why the strain was measured so high for the 1/4-inch anchor as well as the unbonded anchor. That doesn't logically make sense, but we kind of assumed as of right now that that is due to an issue with the strain gauge application. And that's just something that's going to have to be taken into consideration when I get around to actually testing my experimental beams. So I just touched on this, but I would like to still summarize the main findings that we found so far from my SLC beams that were tested in preliminary testing. As I mentioned, we found that the fiber anchors increased the beam strength from about 37% to 100%. The strain utilization increased from about 500% to 700% between the anchored and unanchored beams. And then finally, what was really interesting to see was that the fiber anchor diameter size really did not have any significant effect on the overall beam strength. I'd like to wrap up with giving some acknowledgements to, first of all, Fife, who is the company who provided me with all my materials for this research, and also my lab manager, the structural lab manager at University of Delaware, Gary Wenzel, for helping me with this project. Thank you everybody for listening, and I'd be happy to take any questions now if you guys have any.
Thank you so much for sharing all this. Very interesting. So I'll open the floor for questions.
If I may, a question, Arnold here. Sophia, thank you for sharing this interesting experimental results. So talking about this strain utilization increase, so I guess that will be a great news for FRP beams, because that means that the ductility of this beam will be hugely increased. Would you agree?
I'm sorry, can you repeat that again?
Well, I'm just trying to kind of interpret your results from a component ductility point of view, because when your ultimate strain of the FRP bar increased so much, then that means the overall ductility of the beam will be increased. Would you agree with that?
Yes, I'd say that. And then also one of the another takeaway from that is, as the strain increases, it's also indicating that you're getting more use out of the material itself. And that's one of the great things about the anchors, is then you start to see, compared to an unanchored beam, that you get a higher increase in the strain and you get more use out of the properties of the material. So not only the increase in ductility, but also more use out of the material. All
right. Yeah, maybe another question, maybe you already mentioned it during your presentation, but I probably missed it. Mm-hmm. What is the primary purpose of your accelerated conditioning component of your experiments? Are you trying to look at the overall residual life, or what is the purpose of those accelerated conditioning?
The point is for bond retention. So we can research the bond retention of the accelerated condition beam in comparison to the standard lab beam by just taking the average strength of the condition beam and dividing it by the average strength of those.
Okay. Are you looking at the overall degradation of the bonding capacity or not?
I mean, yeah, that's probably one of the things that we're going to end up looking at is how the bond does degrade over time. At least just at that set 3,000 hours that's going to be exposed, we aren't varying the time duration, which is something that I guess would be interesting to look at, is how that bond degrades over time. But yes, I do believe that is something we're going to look into.
Okay, thanks. That's great job. Yeah, thank you.
Thank you for the questions. I appreciate it.
Any other questions?
I'll ask a non-structural question. I mean, I think that this type of treatment seems quite important in terms of extending the service life of facilities. I am curious, so beyond that benefit, I am curious how the carbon reinforced treatment that you are proposing, how it compares to other alternatives that we might have to essentially correct these problems, basically without having to replace the entire structure.
It's a good question. To be honest, I'm not too familiar with other types of repair methods as of right now, other than, as I mentioned, using different forms of fibers in the composite material. And as far as I'm aware, and as I kind of mentioned earlier, carbon is one of the material or one of the fibers that has the highest modulus of elasticity, which is why it's being used currently rather than other fibers such as basalt or aramid or Kevlar. But as far as my knowledge goes on repair methods, really all I've been able to look into so far is the use of composite materials, but that's all I would have to say about using carbon over other fibers. Does that answer your question? Okay.
Yeah, thanks. I mean, sorry. Thank you, Sophia, and thanks for an excellent talk.
Thank you.
So I had a question. So I wanted to know what, I guess in terms of like moisture exposure, I could imagine there are many levels of moisture exposure. So like there might be acceptable, tolerable levels. Are we talking about like moisture exposure that causes debonding? Is this like very extreme exposure to water? Like what kind of amount is, I guess, tolerable? Do you know?
I'm not sure. Would you be able to specify, do you mean in terms of duration to exposure and heating, or what do you?
Yeah, is it kind of like a chronic exposure to moisture, or is it kind of like massive flooding events that is causing that might cause debonding?
I see. I see what you're asking. I wouldn't say that it's necessarily chronic exposure like you mentioned, but I think it is more so just trying to replicate what long-term exposure, like exposure to rain or exposure to humidity, factors like that, rather than something that's more catastrophic. And it's just trying to replicate how the bond will deteriorate over time from effects like that.
Okay.
And there are, just to point out, there are also many other types of accelerated conditioning that can be tested. It's not just moisture exposure that can affect the bond. There's also things such as, or tests such as UV radiation exposure. There's de-icing salt exposure. There's diesel fume exposure. There's so many things that can affect the bond between CFRP, but we are just specifically focusing on moisture exposure.
Thank you so much. So I guess, are there any other questions from the audience? Also, if there were any questions for Amir that we didn't get to address with time, if there's any questions on that. Okay, so if there's no more questions, in that case, I'd like to thank both Amir and Sophia for sharing their research and giving excellent presentations. It's been a pleasure to hear from you all in your work, and I hope that we can continue to collaborate and learn from each other like this.
Thank you everyone. Thank you, Adrian, for organizing.
Yeah, of course.
you.
Thank you.
All right. Thank you, Adrian.
Yeah.
Yeah. Take
Thank
care.
you.
Have a nice weekend.
Take care. You too.